Hi everyone, today we want to move on to a new topic, heap sort. Okay, well let's do a very quick review on the master theorem. So for the master theorem, our goal is that if we have a divide and conquer algorithm, and for this divide and conquer algorithm, well we assume that it divides the full set of the problem into a number of the subproblems, and for each size of the subproblem, that the size will be n divided by b. And after that, there will be some additional costs after or before we have done the divide and conquer, and usually we call that the aftermath part of the recursion. Okay, and the cost of the aftermath, well, we assume that to be the fn. Okay, and then after we have those information and we want to put this divide and conquer the Tn like this. So Tn equals A multiplied by N divided by B and plus Fn, which is the aftermath. And after that, well, we only have to compare two things. Well, Fn and then N powers N log Ba. Okay, you want to figure out if Fn and the n to the log Ba, they grow equally fast, or Fn is faster or Fn is slower. And after figuring this part out, and then you will be able to see which case it might be. So case 1 or case 2 or case 3. And for case 3, it will be a little bit tricky. Well, after you see for the first part, if Fn is omega n to the log Ba, and this means Fn grows faster than n to the log Ba, and after that you also have to prove this part in order to really use the case 3. Okay, and after that we talk about the sorting algorithm so far we have discussed, and in our formal lecture we discussed two sorting algorithms. Well, they are the merge sort and then the insertion sort. Well, for the merge sort, well, the good news is the worst case running time will be O n log n. So this is faster compared with the insertion sort. And insertion sort, the worst case will be O n squared. Okay, well, but what is the cool thing about the insertion sort? Number one, is this sorting in if we want to sort with the insertion sort, and then that is the sorting algorithm in place. This means you don't have to require extra memory space from the operating system. So that's the first good thing. And the second thing is, well, in the best case of the insertion sort, think about that. So if this list is already pre-sorted, and then what do we say? Do we have to do any of the shifting? No, right? And do we have, when we include one more value into a sorted portion? Well, if this new value is already at the right place. So do we have to do a lot of comparison? No. Do we have to do any insertion in the best case? No. Okay? So in this case, well, in the best case scenario, and the insertion sort will be faster than merge sort. Okay, so in the worst case, of course, merge sort is O n log n, and the insertion sort is O n squared. But in the best case, well, actually insertion sort is faster. And what else? Well, remember when we are doing the merge sort, we have the divide and conquer. When we are using divide and conquer, what does that mean? This means we are using recursions, and for the recursions, remember they are function calls. Right? So when we are doing the function calls in Python, and there will be extra costs, we have to trigger another function call, and then we have to send the parameters, and we also have to maintain extra memory space. So this will be some extra cost for the recursion. So actually, if you have one algorithm and two implementation, one with recursion, one without recursion, and then you will find that in most of the cases, the version without recursion will be faster. What does this mean? This means the recursion will be slower simply because there are a lot of the function calls behind the scene. This is also another advantage of the insertion sort. Okay, so today we want to move on and we want to talk about the heap sort. So what's the cool thing about the heap sort? So number one, we want a fast algorithm. right? We want to have a O in log n if we can choose between O in log n and n squared. And what else? Well, we also want to sort in place. We don't want an algorithm that keep on requiring memory space from the operating system. And then we have the heap sort, and the heap sort has both of those features. Okay, so what is a heap? Well, a heap is this structure, and this is a complete tree. So how do we define a complete tree? Well, a complete tree, oh, by the way, we are talking about the binary complete tree. Okay, so there could only be up to 2 possible children nodes for each of the parent node. And then for a complete tree, well, you can consider that as a tree structure from the top to bottom. And then if we fill in the nodes from top to bottom, and on each level, we fill in the nodes from the left side to the right side. And then we have a complete binary tree structure. Okay, so let's take a look on this one. So we want to fill in the nodes from top to bottom. Okay, so we fill in this layer, we fill in this layer, the second layer, and then the third layer all full, and then the last layer not full, but we fill in the nodes from the left side to the right side. Okay, we have the 2, 4, and 1, and then we stop here. So there's no empty slot before 1. Okay, so before 1, we have been filling in the nodes from top to bottom, and for each layer or each level, we fill in from the left side to the right side. So yes, this tree structure is a complete binary tree. Okay, and in our textbook, we call them the nearly complete binary tree because, well, if we fill in all the remaining nodes on the last level, and then this is really 100% complete binary tree. Okay, well, and usually what we can see is, well, for the unfilled level of the slots, we can just assume that they are empty pointers. So there is still a right child to 7, but we assume that that is just a null node or a empty node. Okay, and for the heap, how do we really store the heap in a tree structure? And of course, you may think about the binary tree, right? And if you have been in a data structure course, and I'm pretty sure you know binary tree. But for the heap, since we know they are complete binary tree structure, and actually we can put all the values into an array. So we just put all the values from top to bottom, and then for each level from the left side to the right side, and we put all the values into an array, and then we have this array like this. And then if we want to put all the values into a binary tree structure, and then we will have a heap. So, well, making use of the completeness feature of the heap, we are able to represent a heap in an array structure, which is much easier. Okay, and then since we can put the heap into an array structure, so what cool thing do we have? Well, where is the root? Well, the root is the very first value, right? And remember, in our textbook, we always count the indexes from the 1. So we can say, okay, the root will be the A1. Okay, and if we have a node in the middle, which is AI, and then how do we find the parent? So the parent is the A floor divided by 2. So this is the integer division or a floor division. Okay, and then how about the 2 possible children of of I? And then that they are the index 2i and 2i plus 1. So if you have the I, and then I floor divided by 2, you have the parent, and then the 2 children will be 2i and 2i plus 1. Okay, so this is a cool structure. And now let's talk about heap. So another property of the heap is we want to enforce a rule. The rule is for each node, for each parent-child pair. So a parent and child, and then the rule should be the parent is always greater or equal to the value of the child. And this should be true for all the parent-child pair. Okay, so we want to enforce this rule for all the possible nodes, and then we have a max heap. So, well, in this book, we only talk about the max heap, and of course, if you want to reverse the rule, so if you want to enforce the rule, an opposite rule, saying the parent is always smaller or equal to the child, and then you will have a mean heap. But anyhow, in this lecture, we only talk about the max heap. Okay, so if we can enforce this rule, we are doing a max heap. And then my question is, where is the largest value in a heap after the heap is done in the right way? So where is the largest value? So think about that. Well, if the parent is larger, then all the parents in the heap is greater than their children, and then the largest value, it will go to the very top. So the largest value will be the root. Okay, and let's see this question. The smallest value in the heap as an array is the last value. Is that true or false? So we know the largest value is the root, and this means that the largest value is the first value in the array. But how about the smallest value? How about we see this example? So on this example, and you will find 1, which is indeed the smallest value, and it is the last value in the array. So can we come to the conclusion that the smallest value will be the value at the tail or at the end? So think about that. The answer is no. Why? Well, let me give an example. Say if I change this 1 to 6. Okay, so for this one, I change it to 6. So is this still a valid max heap? Think about that. So this one, this one, I changed it to 6. So the answer is yes. I didn't violate anything, so 16 is greater than 14, 14 is greater than 7, and 7 is greater than 6. So I didn't break anything. However, if I change this 1 to 6, and the smallest value will be 2. So in this case, it's not guaranteed the smallest value will be the last value in the heap. Okay? So let's see. Well, and now we want to move on and we want to define the height of the heap. So the height of a node in the tree equals the number of the edges on the longest downward path to a leaf. Okay, so this is the height of a node. And then let's move on. Well, we want to define the height of a tree or a heap. So the height of the tree is the height of the root. So if the root go down by one direction, go down by one direction, there are 4 edges, and down but to the other at the other side, and then the height is 3. And then we want to take the higher one, so the height will be 4. Okay? And so what is the height of an n-element heap? Okay, so let's start from the easy case. So how about there's only one node? So if there's only one node, and then we are talking about the longest number of the edges, the longest path, and then we are counting the number of the edges, and then there's 0 edge to count. So if there's only one node, and then the height of this heap is 0. So how about we have 2 or 3? So if we have 2 or 3, and then we have one parent, and then 1 or 2 children, right? So in this case, what's the height? The height will be 1. Okay, let's move on. If we have 4, 5, 6, 7. If n equals 4, 5, 6, 7, and then what is the height of this heap? So if we have 4 nodes, 5 nodes, 6 nodes, or 7 nodes, this means we have one level, the second level, and then the third level. So we have 3 levels, but remember we are counting the number of the edges for the longest path. So 2 edges, and then the height will be 2. Okay, so do you see any pattern? So if we have a n element heap, and then the height will be the log n round down. Okay, do you see that? So if you have 2 or 3 nodes, and then what's the height? The height is 1. And then we have 4, 5, 6, 7. What is the height? The height is 2. Okay, so it's always the log 2n, and then we want to round down, and then we have the height. Okay, well, it is really nice because for most of the operations, well, the height of the heap will be the maximum of the operations we need. So, well, the height of the heap, that is the important factor we are going to use later in this class. Okay, well, and I think I have covered a lot of content. Well, we talk about what is a heap, and then the definition and the features of the heap, and we also talk about the height of the heap. So I want to stop my video here, and the next video we want to talk about one of the most important operations, that is the Heapify. Okay, so I will see you in the next video.